What's up, chemistry class? Welcome to some bond energy, bond enthalpy notes. There's two things I'm going to need you to have with you: calculator, and I'm going to pull it up. I meant to pull up this earlier. This reference sheet, which is on Schoology, or you can kind of just take a screenshot of this right now and kind of use it later. But we are going to use it. It's just going to be on my other screen, so you're not going to see it anymore for this video. But in any case, let's get rolling. Okay. Last week, or kind of the previous lesson we did, we talked about how energy itself, especially heat transforms, can be mostly two things. They can be endothermic or exothermic. Endothermic meaning absorbs energy. Specifically, we talked last week about heat energy. It gets cold. Or a energy change can be exothermic, meaning it loses heat. It releases heat into its atmosphere, or releases energy. It could most likely be in the terms of heat, though. Now let's change, instead of using just heat as our vocab, our words to talk about energy change, let's use enthalpy. So enthalpy is the measurement of the total energy in a system. Could be all things included. Heat, could be movement, could be stored energy, could be whatever type of energy you want. Enthalpy is the total energy within a system. Now, to determine if a system is endothermic or exothermic, we have to use this kind of equation down here, and let's unpack it. So if the change in enthalpy, so I'm going to kind of write it as we go through it. The change in enthalpy, if it's positive, so if delta H is was positive, I'm writing the wrong one. If delta H is positive, this means, I wrote that in the wrong spot again. Let's try that again. If delta H is positive, it absorbs energy. If delta H, or the change in enthalpy, is negative, means it releases energy. It's exothermic. So let's put this in terms of reading this equation right here. So the change in enthalpy is the sum of the bonds broken. So I'm going to put B minus the sum of the bonds formed. So what we're going to do is we're going to compare the chemical bonds that are broken in the chemical reaction to the chemical bonds that are formed in the chemical reaction. From there, we can predict if the reaction is going to be exothermic or endothermic. So let's do a little bit of a kind of pulling up those graphs that we have. Now, you don't have to redraw all these graphs. You kind of reference it, what you have from last week. But if delta H is positive, there you go, that's going to be endothermic. If delta H is negative, that's going to be exothermic, so on and so forth. Both of these are going to have some sort of activation energy, right? The energy it takes to activate or to get the chemical reaction started. We're not really looking at that too much. It is there, but we aren't going to be looking at it in our calculations. We're only looking at what I have as drawn as the red arrow here, showing the change in enthalpy. So we're going to look at the energy of the reactants, compare it to the energy of the products, and then just subtract the two. So let's kind of just do that. Let's compare energies. So how do we do that, though? Let's take a chemical reaction, super simple chemical reaction that we already know, where hydrogen gas reacts with chlorine gas to produce hydrochloric acid, or HCl, or this would be hydrochloric gas, or hydrogen chloride gas. A couple different ways you could say it. If we look at the bonds and we actually draw those molecules out, remember, H2 is actually H bonded with another H, right? So we have one hydrogen bond here. Notice that's drawn in red. Chlorine with another chlorine, we have a chlorine bond there. And what does it form? It forms two hydrogen chlorine bonds. Now, way back, we talked about electronegativity, about how electrons are shared or taken. the amount of energy stored in a bond really is pulled from that number. As what is the electronegativity? How tightly are those atoms holding on to those electrons? If it's a loose connection or loose bond, you could say it's a very low energy bond. If it's a very tight connection, it's a high energy bond. So let's look at what we have going on here. The change in enthalpy for the reaction equals bonds broken. What bonds are we going to break? We're going to break one hydrogen to hydrogen bond and we're going to break one chlorine to chlorine bond. So that's what we're going to break. Let's put that in brackets. And this is our bonds broken. Okay, those are the chemical bonds we broke. Let's do it in a different color about the bonds formed. So let's put it in a bracket around the bonds formed. And that's going to be 2 hydrogen chlorine bonds. Pretty straightforward, right? Excuse me. Thank you. I was hoping that's timed perfectly with somebody saying bless you. If so, let me know. So, we looked at the bonds broken. We looked at the bonds formed. All we need to do now is plug in the energy values for those bonds. Well, if we look at hydrogen-hydrogen bond, it stores 436 kilojoules per mole. So we're going to do 436 plus 243 for chlorine to chlorine minus 2 times 432. That's it. All we're doing is looking at the energy stored in those bonds. Let's do a little bit of math. Remember I said you need your calculator nearby. Let's do 436 plus 243. That gets me 679 minus 2 times 432. That's 864. 679 minus 864. That means this chemical reaction is going to have a change in enthalpy or change in energy level of 864 is negative 185 kilojoules per mole, which means this chemical reaction is going to release this much heat energy per mole. So this is going to be an exothermic reaction. We would expect this to release heat because it's going from a high energy molecules to a lower energy molecule. Okay, let's move on to the next one. And I'm going to pull up my reference sheet. I'm going to look at it and pull numbers from those. So the first thing we need to do is we need to draw our, first off, we need to balance the chemical reaction. So if we do that real quick, let's balance chemical reaction, put a 2 here, put a 2 there, boom, done. 2 oxygens left, 2 on the right, 4 hydrogens left, 4 hydrogens on the right, boom, done. Now let's draw the chemical molecules. Let's draw molecules. Oxygen bonded to oxygen plus hydrogen bonded to hydrogen yields or gives you HOH. Now, here's where some old school stuff is going to sneak in, is because we have to draw the Lewis diagrams for these molecules. Now, if you need a refresher, maybe look back in your notes, but I'm very quickly going to draw the Lewis diagrams for these molecules. If we calculate it up, oxygen is going to have 12 valence electrons. Actually, let's pull my periodic table up and let's do this together. ptable.com. oxygen's going to have, so 12 valence electrons total. That's 1, 2, 3, 4. Drawing our dots. Now this might be ringing a bell. Oh, Lewis diagrams. We give it a bond, draw our dots. Does it have 12? And that's 2, 4, 6, 8, 10, 12, 14. We have too many electrons, meaning I actually need to erase some and draw a double bond. So oxygen has a double bond here. Hydrogen, we need 2 valence electrons. There's your 2, done. And if we look at H2O, that's going to be 8 valence electrons in total. So that's going to be 2, 4, 6, 8. It is done. So our Lewis diagrams are drawn. We're good. Like I said, if you need more practice on that, I'm going to walk through these examples. You're not going to be on your own. But if you're good, cool. If not, just make sure you ask some good questions back in class. But we've drawn our diagrams. We are now ready to look at our bonds. Remember, the change in enthalpy of a chemical reaction equals the sum of the bonds broken minus the sum, oh, that was a really ugly sum, minus the sum of the enthalpy of the bonds formed. Well, what bonds did we break? We broke 1 oxygen double bond, and we broke, how many hydrogen bonds did we break? We actually broke 2 of them, because if we look at our chemical reaction, we didn't break 1 hydrogen molecule, we actually broke 2. So I'm going to erase this. There we go. Because for every 1 oxygen molecule, we have 2 hydrogen molecules to produce 2 waters. So let's make sure we got, or at least highlighting what we've done so far. So we've got our 1 oxygen double bond taken care of. We now need to include our hydrogen bonds. And last one, our hydrogen-oxygen bonds. So let's try writing these out and see if we got it right. So bonds broken, that's going to be the oxygen-oxygen double bond plus 2 of the hydrogen bonds. Let's color code that, make sure all we're good in the same boat. We're going to make that red. Hope the color code is helping. Oh, minus the sum of the bonds formed. Well, that's going to be 4, 1, 2, 3, 4 hydrogen-oxygen single bonds. There we go. Ooh, this is a good question. This is real chemistry. I like this stuff. Okay, so delta H reaction. I'm going to look at my reference sheet. So let's, I'm just going to pull it up. Oxygen-oxygen double bond. Let's find it. We got double bonds. Oxygen-oxygen double bond is not on this list. There it is, O2 right there. 495. So that's going to be 495 plus 2 times hydrogen to hydrogen. Where is that going to be at? Hydrogen to hydrogen is 436. 436 minus 4 times hydrogen to oxygen. Hydrogen to oxygen right here. 463. Ooh, good stuff. Let's try it out. Bracket 495 plus 2 times 436 minus 4 times 463. And I get an answer of negative 485 kilojoules per mole. So 495 plus 2 times 436 minus 4 times 463. Looks good with me. This is another exothermic reaction, meaning it's going to get hot. It's going to release a lot of heat energy. Cool. Let's do another one. What's our time at? I don't even know. We're looking good. All right. Let's look at this chemical reaction. Well, first off, it's combustion, so clearly this should be exothermic. When you light something on fire, a lot of heat energy released. Now, I'm going to draw, first off, we got to balance. Well, let's see what we got. We're going to put 2 here, because there's going to be 4 hydrogens, carbons look good. So now I have 2, 4, put a 2 there, and I think that's going to be it. Looks good to me. Let's draw the molecules now. We got CH4. If we were to count up our valence electrons, we would need 8 valence electrons for CH4. Boom, that one's good. Plus 2 oxygen molecules. Now we just did oxygen in the last example as a double bond, so we know this one's good. There's just 2 of them now. CO2 is going to be COO. The valence electrons here are in total are going to be 6, 12 plus 4. So this would be 16. So if we do, let's draw our dots in. Everything gets 8. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that tells me we have too many electrons. So I'm going to erase some of my dots. We need to put some double bonds in. Two, 4, 6, 8, 10, 12, 14, 16. So now CO2 is good. And we only have 1 of them, so it looks good to me. And then we have 2 water molecules, just like the last example. So I'm just going to draw these, and we're going to assume they're going to be good. Okay. We've drawn our molecules. We've drawn how many we've had. Now let's look at our change in enthalpy of the reaction. So bonds broken, the sum of the bonds broken minus the sum of the enthalpy of the bonds formed. So what do we have? For bonds broken, we have 4 CH bonds plus 2 oxygen double bonds. Let's go with me so far. Minus 2, well, I wrote that, there we go. Minus 2 carbon oxygen double bonds and 4 hydrogen and oxygen single bonds. Looking all right. Let's now plug and chug some of our numbers in. So 4 for CH. I need like 3 screens. If you want to get me some bonus points, get me a computer that can have 3 monitors. There you go, extra credit. I'm just pulling these numbers from the data table. 2 times C oxygen double bond. Excuse me. That's going to be 799 plus 4 oxygen hydrogen bonds is 463. Cool, we're looking good on time. We should be able to get all of these example problems done in 1 class period. So 4 times 413, I'm going to do in parentheses, 4 times 413 plus 2 times 495 minus 2 times 799 plus 4 times 463. Now, if I did this right, this should be a negative number. Looks good with me because it's combustion. I mean, it should get hot, right? Absolutely, it's going to be exothermic. And it's actually going to be a pretty big exothermic reaction. So, boom, there we go. Exothermic, and we are finished. Let's do one more example. I think we got one more example in ours, right? No, we do not. We did our 3 and we're done. Okay, if you guys have any questions, please let me know. My apologies for not having any examples in here for endothermic reactions. There is a very good conversation into why you find more exothermic than endothermic reactions. But you guys are awesome. Stay awesome. I will see you in class here soon. If you have any questions about these notes, please write them down and we will address them in class the moment I see you. Take care.